Okay, hello everyone. So, in the last lecture, we introduced a general framework for um, approximating uh, any equation with finite differences scheme. So this was a very general way of doing that with kind of arbitrary number of points that you can select, and then uh, just requiring the consistency requirement of the um, finite difference schemes, we were able to find this general matrix in which we could find the those coefficients, gamma coefficients, that are required to kind of find the finite difference schemes that is of interest for us. Okay. And now, in this lecture, I want to make some remarks about this, some points about it. And after that, we are going to solve one example of it. And then we will talk about some standard finite difference approximations that are typically being used in the in the community. And after that, we will show one example of like kind of calculating truncation errors. So we have used like Taylor series here to kind of show this general approximation, and then we will use an example of truncation error calculation, how you can truncate, how you can calculate those truncation errors for any type of given finite difference approximation. Okay, so we talked about different points, like if you have more points than the order of the derivative that you are seeking, or less than that. If you have less than that, you will not have any solution. You cannot approximate any finite difference, any derivative, if your number of points that you want to evaluate the values of that function is less than the order of the order of the derivative plus 1. Okay, and if it is greater than that, your number of points, you will have many solutions. Okay, so these were some stuff, a summary of what we learned last time. Okay, so now let's get started today. So I'm gonna give some remarks. So the first remark is a consistent finite difference approximation for an mth order derivative using p points requires, based on what we learned here, it requires for the number of points to be greater or equal to m plus 1, the order of the derivative plus 1, or your number of points should be just greater than the order of the derivative that you want to approximate. Okay, so this is one remark we learned here. Okay, so as you see, if it is greater than that, plus m plus 1, we will have infinitely many solutions, and if it is equal, we are going to have unique solutions. So in order to have a consistent finite difference approximation for an mth order derivative using p points, the number of points should be greater than the order of the derivative. Okay, so this is the first remark. The second remark is if p, the number of points, equals to the order of the derivative plus 1, approximation is generally order delta x. Okay, it's generally order delta x, meaning it is first order, right? And we can have higher order accuracies too, right? So the third remark says if p, the number of points, is greater than m plus 1, we can obtain higher order approximations depending on the order of accuracy. Made a mistake here. We can make approximations, higher order approximations. I forgot to mention this, that by forcing, how can we do that? By forcing higher terms like other equations to be 0, like fm plus 1 to be 0. We didn't write it here, so we only wrote up to fm equals to 1, right? But if we force other equations to be 0, like fm plus 1, and depending on the order of the accuracy that we want to seek, the order of, let's say, south accuracy, we can force fm plus 2 equals to 0 and etc. So if you want to get higher order accuracies, we have to go further. So we have to force fm plus 2 to become 0, and then fm plus 3 to become 0, and all those equations have to become 0, so we can get higher order accuracy. So this is how you can get and obtain a higher order accuracies than just the first order, which is the order delta x, which is generally when you do it with p equals to m plus 1. Okay, so these were some general remarks, so you have to have them in mind. And now I want to give you an example. So I want to solve an example using this general finite difference approximation that we talked about. Okay, and this is a very generic example, so you can do it yourself with other type of approximations as well to become more proficient in this approach, in this type of approach. Okay, so express, the example states to express d square u over dx square at I plus 1. We just want to do it not at I, so become a little bit different. At I plus 1, using these 3 points, xi minus 1, xi, and xi plus 1, using these points. Let me write it this way. Let me put it here. Example. So express, let's write it like this, right? And yeah, or maybe just express is enough. It's good. So we can say express an approximation for d square u dx square using these points. So this is the problem that we have, the problem statement. And so let's get started. So let's get started with this general approximation that we had. So what we learned last time is that we can write any and all derivatives in finite difference based on this sum, okay? So we know the points, we know what points we have, so I can just write it as this. I can write d square u over dx square at I plus 1 can be written as gamma I minus 1 ui minus 1 plus gamma I ui plus gamma I plus 1 ui plus 1, right? So this is the way we can write this down. So now the question is, what are these gammas? So we have to find these gammas here in order to be able to approximate it. So why I wrote it this way? Because the question asked me to do so. Question asked me to approximate it at xi minus 1, xi, and xi plus 1, right? So that is why I wrote it this way. And this is just at the d square u over dx square evaluated at I plus 1. You should note that. And so now the next step is I want to find these gammas. And if I find those gammas, then the question is answered. So let's get started. I want to write those equations for f0, f1, fm, these matrix. Actually, I want to create that matrix. So let's just start with f0. So f0, what was f0? If you remember, f0 was just a summation of all the gammas, right? So it was, if you multiply this by that, you will get sum of all the coefficients. So it states gamma I minus 1 plus gamma I plus gamma I plus 1 should be 0. So this is the first requirement for consistency. The second one was f1, which is going to be gamma I minus 1 multiplied by what? So if you remember, this is the general formula for fm. So it's going to be xj, or let me just show it here. It's going to be xj minus x star times gamma j, right? So what is xj? So let me write this down. xj is going to be xi minus 1 minus x star. What is x star? It's xi plus 1. So it's going to be xi plus 1 plus the second term, which is gamma I, is going to be what? Is going to be xj, which is going to be xi minus xi plus 1 plus the third term, which is going to be gamma I plus 1 multiplied by xi plus 1 xj minus xi plus 1. Okay, and the whole thing equals to 0. So let's see what it is. So these two are going to cancel out, right? So this is going to be 0. And this one, I can just write it as minus 2 delta x. And this one, I can just write it as minus delta x, right? Just a simplification, if you assume they are equidistant. So I can write this down as gamma I minus 1 multiplied by minus 2 delta x plus gamma I multiplied by minus delta x equals to 0. What is the third equation? The third equation says f2, which is going to be gamma I minus 1 multiplied by Now we have this one squared over 2 factorial. So I'm going to get 4 delta x squared over 2 factorial plus the second one, which is going to be gamma I, this one squared over 2 factorial. So I'm going to get delta x squared over 2 factorial plus gamma I plus 1 times 0, right? So this is 0 equals to 0, right? So this is the second term that I have. This is this equals to what? Because this is fm plus 1, right? Let me see. This is fm, right? F and m here is what? M here is 2. Right? This is dm square, yeah? So this is gonna be, let me just write this down here. M is 2. So, and this is fm, which is f2, so this should be 1, equal to 1, okay? Based on what we have here, fm equals to 1. Okay? So, this is gonna give me that matrix that we had, so I can just simply simplify this and solve this without converting it to a matrix. I can say gamma I from the first equation, I can just say gamma I plus 1 equals to minus gamma I plus 1, right? From the first equation here. Second one, from the second equation, I can say gamma I equals to minus 2 gamma I minus 1. And third equation, I can write it down as, I can just put this 2 to the other side. And also 2 over delta x squared to the other side. And I can write it as gamma I minus 1 times 4 plus gamma I equals to, I bring the 2 over delta x squared to the other side, so I'm going to get 2 over delta x squared, right? And then from these two, I can find gamma I minus 1. So let's just substitute in the second equation. I'm going to have 4 gamma I minus 1. And instead of gamma I, I'm going to write this down here. So I'm going to write it minus 2 gamma I minus 1, which is going to be 2 gamma I minus 1 equals to 2 over delta x squared, right? So I can simply find what is gamma I minus 1. So gamma I minus 1 is going to be what? It's going to be 1 over delta x squared, the first finding, then I can find gamma I from here. So gamma I is going to be minus, sorry, this just needs a little bit recharge, but gamma I is going to be minus 2 over delta x squared, right? From this the second equation, we can just learn that. So it's going to be minus 2 over delta x squared and And gamma I plus 1 is gonna be, if you just put these here, so minus gamma I minus plus 1, what you are gonna get is simply 1 over delta x squared. So we found these solutions here. Okay, so let me just write down, we found these coefficients here, so let me write down the exact approximation, the approximation for this points, these points. So it's going to be d square u over dx square evaluated at xi plus 1 is going to be approximated, can be approximated as, the first one is, so I'm going to use this formula here, gamma I minus 1 times ui minus 1. So it's going to be ui minus 1 minus 2. The second one is gamma I minus 2 ui, and then plus gamma I plus 1 times ui plus 1, which is going to be just ui plus 1, and all of them over delta x squared. So this is going to give me the approximation that I was seeking. Right? So approximation of d square u over dx square evaluated I plus 1 using these 3 points.